Good afternoon, everyone. So today is the week 6 of this tutorial session on this course Principles of Modern CDMA, MIMO, OFDM wireless communication. So today we are going to solve some of the questions based on CDMA and MIMO, which is taught in the week 6, and also we will cover some of the concepts of this week 6. And this video will be recorded and it will be uploaded on YouTube, and the link will be shared in the NPTEL portal. First, we'll start with in the last lecture, we have already studied about the basics of CDMA. So today we will study about the multi-user CDMA and the signal to noise and interference ratio, SINR. Today we will study about multi-user CDMA. Let's suppose A0 and A1 denote the symbols of the user 0 and 1. So for user 0, the symbol transmitted is A0. For user 1, A1. And the power, like the transmit powers of the user, be denoted by expectation of mod of A0 squared for user 0, that is, let's suppose P0, and for user 1, it is P1. So this is the transmit powers. So on the downlink, like at the receiver end, the signal X0 n of the user 0 is derived by X0 n is equal to A0 into C0 into n, as we have studied in the previous lecture. So C0 n is the code for the user 0, and A0 is the symbol for the user 0. And similarly, X1 n will be A1 C1 n. And we know that the Xn is the summation of X0 n and the X1 n. So the received signal will be X of n plus the noise. So noise is here W of n. Noise is IID noise, and we can write x naught xn as x naught n plus x1 n. So this will become a naught c naught of n plus a1 c1 of n plus w of n. So this is our received signal, and this is our noise, awgn noise. So for this, the mean of this awgn noise will be 0, and the variance will be sigma square, sigma n square. So we can also write here expectation of w of n1 into conjugate of n2. This value will be this value will be 0 if n1 is not equal to n2, and if n1 is equal to n2, this will be sigma square. So now, for user 0, we will multiply, like as we have studied in the previous lecture, that for user 0 will multiply with the code, uh, we will use code C0 to recover the signal. So R0 is equal to 1 by n into yn into code of user 0, and I is equal to 0 to n minus 1. So now this we can write as 1 by n like when we substitute the value of y of n, then we can expand this derivation, expand and derive like this, wn into c naught of n, because here our we are using this equation y of n, this equation we are using here. Here we are substituting from 1. Now this is our desired signal for user 0, and this is our interference signal, and this is our noise. Now the desired part, desired signal, we can write as 1 by n summation of a naught c naught n into c naught n. So this will become and we know that this codes are orthonormal, so the magnitude square will be 1, so it will become a naught 1 by n summation of I is equal to 0 to n minus 1, 1. So after summing 1 for the n times, it will become n. So it will be a naught by n into n. So it will be a naught. Now the interference part, and this we can write as a naught r of, so basically r of 0 0 of 0 is the auto correlation of the spreading code C naught n of the user 0. Now coming to the interference part. So this is equal to 1 by n summation of I is equal to 0 to n minus 1 a1 c1 n c naught n. Actually this is this value a1 c1 n into c naught n. So this we can write as a1 we took outside, so here it will become c1 n into c naught n. So as we know that this is a codes are orthogonal, so whenever c1 n into c naught n will become 0, so we can write this as a1 of autocorrelation between 0 to 1 of 0, and the power interference power is given as expectation of I1 squared. Let's suppose this is our I1. So finally we will get expectation of A1 R01 . So expectation of A1 mod square is P1, that is power of symbol 1, and expectation of R01 will be 1 by n, as we have derived in the previous lecture. So this will become P1 by n. And similarly for the noise we will get for noise power, when we'll derive, we will get sigma n squared by n. So finally our SINR, that is signal to interference noise power, this SINR value will be first the signal power divided by interference power plus noise power. So we will get P naught, signal power is P naught, and the interference power is P1 by n, and plus the noise power is sigma n squared by n. We will get P naught into n divided by P1 plus sigma n square. So here you can see this n. So the SNR is increased by the factor of n, which arises because of the like because the noise and this interference is suppressed by n. So this n came into numerator, and the SNR is improved by the factor of n. So this is the formula for SINR. So we'll solve some questions, and also now let's take like there are k plus 1 user. Consider k plus 1 user, and then we will write the general equation of SINR. So for k plus n user, our yn is equal to a naught c naught n plus a1 c1 n plus ak ck n plus w of n. So we can write this as summation of k is equal to 0 to k ak ck n plus the noise. So here our SINR will be, the above one was for the 2 user, now this is for the k plus 1 user. P naught divided by P1 by n plus P2 by n plus Pk by n plus sigma n square by n. So this will become P naught n divided by summation of k is equal to 1 to k P1, sorry, Pk, and plus the noise power sigma n square. So this is a generalized SINR for the k plus 1 user in CDMA. Now we will see the multipath diversity or the rake receiver. This is also taught in the class. We'll see this concept, and then after that we'll solve questions. Like there is advantage of CDMA that it achieve diversity gain via multipath scatter components. So we can write the received signal yn is equal to h of 0 xn plus h of 1 xn minus 1 plus h of l minus 1 x of n minus l plus 1 plus noise wn. So this can be written as L is equal to 0 to capital L minus 1 H of L x of n minus L plus WL. Now in CDMA signal, like Xn is given as A naught C naught into N. So like we will use that, and Y1 will become A naught C naught of N minus capital L. Sorry, this is small L plus W of N. Just we have substituted Xn is equal to A naught of C naught N. So it is a long derivative, but the finally we'll get like I will directly write the formula. Signal is to noise ratio with maximal ratio combiner will be given as so again this is like improved by the factor of n, that is a spreading gain. So this will come. So coming to the questions now, I will also studied about MIMO system, but we'll solve some questions. Then we will again see the concepts of far near problem in CDMA, and then we'll study about the MIMO system. The first question is a special case of a multiple input, multiple output system with a single receiver antenna and multiple transmit antenna is termed as. So let's suppose there is a single receive antenna and multiple transmit antenna. So for this is a multiple input and single output. So here single receive antenna is there and multiple transmit antenna is there. So the transmit antenna is also called as the input. So that was multiple input and single output. So this is called as multiple input and here single receive antenna. So single output. So this type of MIMO is known as MISO. That is multiple input and single output. So option C is the correct answer for this. Now, in order to overcome the near far problem, so better we will first study the near far problem. Then we will solve this question. Now, like what we have studied earlier, that SINR at the user 0 of a two user CDMA system is given as just P naught, like transmit power of user 0, and P1 by N, that is interference signal power, plus the noise power. Consider a scenario like this is our base station. This is transmit antenna. So there is a user 0 here which have distance d naught, and another user is there that is very near to the transmit antenna. The distance is d1. Now let d naught is equal to a square root of n of d1. So the transmit power of each user at the base station be denoted by Pt, since the radiated electromagnetic power decays at the rate of d square. So the power decay at the rate of d square. So P1 is equal to Pt, transmit power, by d naught square. Pt is our transmit power. And this we can write as Pt divided by, and d naught square will be n into d1 square. And our P naught is equal to Pt by d1 square. So the SINR, after substituting this value of P naught and P1 in this equation, using 2 and 3 in 1, we will get Pt by n d1 square divided by Pt by n d1 square plus sigma n square by n. So this will become Pt by Pt plus d1 square sigma n square. So here you can see this is a strong interference here. As the signal and interference power at the user 0 are of the same magnitude, now the effect of this spreading gain n is lost, and this phenomenon arises because of the strong interference from the user 1. So this is the near far problem in CDMA system. Near far problem in CDMA system. So to overcome this, the power that is transmitted to the different user has to be regulated in the CDMA system. Lower power has to be transmitted to user closer to the base station, and such as the user 1 in the previous example, and higher power should be transmitted to the user 0 which is farther away, that is the user 0. This is termed as the power control in CDMA system. So to avoid near far problem in CDMA system, what can be done? First, lower power has to be transmitted to user which is nearby to the base station. Second, higher power transmission to the user which is far from the base station. So this is known as the power control in CDMA system. This is known as power control in CDMA systems. So now we will solve our question. In order to overcome the near far problem in CDMA system, which of the following strategies can be employed? So power control should be employed as we have studied here, like the transmit power P1 should be less than P naught. Okay, so this is the power control system in a CDMA in which the user which is near to base station, for that power transmitted should be less than the uh, for the user which is located far from the base station. Now the next question is the size of the noise vector at the receiver of 5x3 MIMO system. So before moving into that, better we will study the basics of MIMO system. Then we can solve all the question all together. So MIMO stands for multiple input and multiple output system. So basically, let's suppose this is the transmitter side. So there will be multiple transmit antenna this time, and multiple receive antenna as well. There can be different variation of MIMO, like there can be multiple transmit single receive, or sometimes it can be a single transmit multiple receive. So these are various variation of MIMO system. So there is T transmit antenna here, and R receive antennas. Now let's suppose system with T transmit antenna and R receive antenna. So this is also known as MIMO system with R cross T system, or we can directly write here R cross T MIMO system, because there are R receiver antenna and T transmit antenna. Now let's suppose X1 to XT is the T symbol that is transmitted. Let's suppose X is the symbol that is to be transmitted, X1 X2 dot dot XT. So X denotes the T symbols transmitted from the T transmit antenna. Okay, and XI denotes the symbol transmitted from the ith transmit antenna. Here XI denotes the symbol transmitted from the ith transmit antenna. Okay, now the transmission, like at the receiver end, we will get Y symbol, that is Y1 Y2 dot 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 YR. So this is the like received symbols. This is R received symbols, and Y1 denotes the symbol received from the ith receive antenna. So this symbol X1 to XT is transmitted via channel. This channel we can call as a MIMO channel, and received at the receiver, Y1 Y2 YR. Okay, so the channel is given as H is given as H11, H12, H1T, H21, H22, H2T, HR1, HR2, HRT. So the number of row will be the number of receive antenna, and number of column will be number of column antenna. So finally we can write Y is equal to Hx plus N. So here our Y is Y1 Y2 dot 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 YR is equal to H11, H12, HR1, HR2, HRT. Into X, that is X1, X2 dot 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 XT plus noise. So noise is here N1, N2 and R. So our Y vector is R cross 1, H vector is R cross T, because R column and T, R rows and T column. This is T cross 1 and this is R cross 1. So multiplication of this will be R cross 1. Okay. So in the left side and right side, the dimensions of the vectors are equal. And here for y1 we can write y1 is equal to h11 x1 plus h12 x2 plus so on h1t xt plus noise n1. So in this way we can write the equation for the uh, y1, that is the received symbol y1. So now the question is the size of the noise vector at the receiver of 5 cross 3 MIMO system is. So 5 cross 3 MIMO system is the dimension of H is 5 cross 3. Okay. So here we can see if dimension of H is 5 cross 3, this means number of row in channel is equal to number of receive antenna, and number of column in channel vector is equal to number of transmit antenna. So here number of receive antenna is 5. So number of receive antenna is equal to 5. So the noise vector will be 5 cross 1. The size of the noise vector is 5. So now we'll move on to the next question. The spatial multiplexing is possible in MIMO system. How? Because the parallel transmission can be done in the MIMO system. Even if one transmission is blocked, then the other transmission channel will work here. Now coming to the next question. Which receiver is employed in CDMA system to exploit multi-path diversity? So the answer is C. That is the rake receiver, what we have studied in today's class. Now if the total number of runs in a PN sequence is 128, the number of runs of length 3 is. So number of runs of length 3 is equal to 1 by 2 to the power of 3 into total number of runs. So that is equal to 128 by 8. So answer will be how much? 16. Option C is the correct answer. The size of the transmit vector of 5 cross 3 MIMO. So 5 cross 3 is the channel vector is 5 cross 3. So number of receive antenna is 5 and number of transmit antenna is 3. So X is 3 cross 1. So vector of size 3 is the correct answer for this question. Consider the MIMO channel matrix below 2 minus 1 2 and minus 1 2 2. The corresponding 0 forcing receiver matrix is. So the ZF receiver is given as H transpose of H inverse into H of T. So what will be the H transpose of H? H is given as 2 minus 1 minus 1 2 2 2. So H transpose is equal to 2 minus 1 2 minus 1 2 2. H of H, sorry, HTH. So HTH is equal to, here we can write 4 plus 1 5 plus 4 9 minus 2 minus 4 plus 4 0 minus 4 plus 4 0 1 plus 4 plus 4 9. So this is our HTH transpose. Now inverse of this will be, okay, let's take a new page. So H transpose H inverse will be 1 by 9 final we have to find multiplication with H of T. So this is ZF receiver. The channel is modeled like this. So here HTH is 1 by 9 9009 into 2 minus 1 2 minus 1 2 2. So the corresponding zero force matrix is the option D is the correct answer for this question. So when we multiply this, we will get 18 then we will get minus 9 and 18. So it is 2 cross 2 into 2 cross 3. So it will become 2 cross 3 matrix only. Then it will become minus 9, 18 and 18. Sorry, this is 1 by 81. Because the inverse of HTH inverse is equal to 1 by 81 9009. So now take the 9 common here. So it will be 9 by 81 into 2 minus 1, 2 minus 1, 2, 2. So this is 1 by 9, 2 minus 1, 2 minus 1, 2, 2. So option D is the correct answer for this question. The transmission of multiple information streams in parallel in MIMO system with multiple transmit antenna and multiple receive antenna is termed as, so the transformation of multiple information streams in parallel in the MIMO system is termed as spatial multiplexing. So option B is the correct answer. In a 3x2 MIMO system with IID noise elements, and the noise variance is given as minus 6 dB. So 10 log 10 sigma square is equal to minus 6. So sigma square is equal to 10 to the power of minus 0.6. So this become 1 by 4. So the covariance, the noise covariance matrix is given as sigma square I R cross R. So it is a 3 cross 2 MIMO system. So there is 3 receive antenna and 2 transmit antenna. So it will become sigma square I 3 cross 3. So that is equal to 0.25 identity matrix of 3 cross 3. So option C is the correct answer for this question. So now let's take a special case of the MIMO system. Now what is spatial multiplexing? There are two questions based on this. So let me explain. So let's suppose this is our transmitter side on the base station and this is the receiver side on the user side. There are I link, I1, I2, like that. So here the transmitter can transmit multiple information streams in parallel. So this is known as the spatial multiplexing. Let's take a last question for today class. Consider a MIMO system with R is equal to 3 receive antenna and the noise power in dB is given as minus 3 dB. Consider IID noise elements and find noise covariance matrix. So for this, The noise covariance matrix R can be given as, this is given as sigma squared into I 3 cross 3. So that is R cross R receive antenna. Okay. So R is equal to sigma squared I 3 cross 3. So here sigma squared in dB is given as minus 3 dB. So now we will find the noise value. So sigma squared is equal to 10 to the power of minus 0.3, that is equal to 1 by 2. So the noise covariance matrix is half I 3 cross 3. So that is equal to half 0 0 0 half 0 and 0 0 half. So today we will end the lecture here only. So we have solved some of the questions based on the MIMO and CDMA in today's lecture. In next lecture, we will study more about the MIMO system and we will solve more numerical questions. That is on Tuesday 6 to 8. So today we will end the lecture here only. If you have any doubt, you can ask. And also this video will be uploaded on the YouTube. So you can watch it later also if you could not understand now or missed the some of the part of this lecture. So thank you everyone for attending today's lecture. We'll end the session here.